This is problem 12 from Unit 2, secant and tangent lines and how they relate to rectilinear motion. The average rate of change is the slope of a secant line to the graph, which is delta y over delta x, and so over the interval a to b, the slope of the secant line is f of b minus f of a over b minus a. The instantaneous rate of change is the slope of the tangent line to the graph, which can be quantized by the limit of, as h approaches 0, f of x plus h minus f of x over h. To show an example, the tangent line to a graph is shown here. This graph is tangent to point B because its slope at the given point is the same as the graph slope at the given point. The secant line to a graph can be shown in this picture, and it is the average rate of change from A to B. All of these definitions connect to rectilinear motion. Rectilinear motion is the motion of a particle on a line, and it is normally shown with a position versus time curve, which is the position function of a particle. Speed is how fast a particle is going, direction is where the particle is going, and velocity is the speed and direction of the particle. So if you're given a position function of a graph, you can figure out its speed, direction, and velocity. The initial velocity is the speed and direction of the particle at t equals 0. And then the speed of a particle is faster when the slope of the tangent line to the graph is steeper. And that's if you're given the position function and you want to figure out at what time the particle has a faster speed, you look at the slopes of the tangent lines to the graphs. And to find speed, you use the average rate of change over an interval to find speed over an interval, so the slope of the secant line. For our problem, we are given a graph that shows the position function of a runner, and we are supposed to use the shape of the graph to determine different things about the runner. So first, what was the initial velocity of the runner? So to find the initial velocity of the runner, we are given the position function, and at time t equals 0, t is the horizontal axis. The particle is not moving, and therefore the initial velocity is 0. As you can see, at t equals 0, the initial velocity of the runner is 0. Part B of this problem was the runner going faster at t equals 1/2 or t equals 2. So first we have t equals 1/2, which is right here, and t equals 2 is just a little bit over. The answer to this part of the problem is that t equals 1/2, the runner's speed is faster than at time t equals 2. You can arrive at this conclusion by knowing that speed at a point is the instantaneous rate of change at that point, which is the slope of the tangent line to the graph at that point. So t equals 1/2, the slope of the tangent line is around 2. At t equals 1/2 right here, the slope of the tangent line shown by this piece of paper is quite steep. We could say it was around 2. At t equals 2, the slope of the tangent line is 0. At t equals 2, the particle is right here, and you can use this piece of paper to find the tangent line approximately at this point, which is close to horizontal, which means the slope is close to 0. The steeper slope of the tangent line to the position function means a faster speed of the particle, and therefore at t equals 1/2, the runner's speed is faster. And for the final part of the problem, we have to figure out if the runner is slowing down or speeding up at the given intervals. Over the interval 6 to 8, the particle is speeding up because the slope of the tangent line is steeper. Over the interval from 6 to 8, the slope of the tangent line increases and therefore just continues to get steeper, and the speed increases, the particle is speeding up. From 1/2 t equals 1/2 to t equals 2, the particle is slowing down because the slope of the tangent line is getting more horizontal. From t equals 1/2 to t equals 2, the slope of the tangent line is getting less steep, and therefore the particle is slowing down. Finally, from the interval t equals 2 to t equals 4, the particle is speeding up because the slope of the tangent line is steep. From 2 to 4, the slope of the tangent line is increasing, and therefore the particle is speeding up. So that is the problem from Unit 2, number 12, and I hope you understand it now.